Fireworks are somewhat magical. In the vast space of the sky, the biggest stage in the world, this show of light spectacle and din appears. As viewers, we can experience each explosion of colors and each rain of silver stars which gently fall and burn up in the openness of the sky. In order to experience all of that, a lot of chemistry and physics had to happen first. I would just like to take a closer look at one of these processes now. What, for example, do physics actually say about the emission of light in fireworks? Today, the physicists explain it by the so-called quantum leap. To put it simply, this works as follows. Caused by the explosions, the atoms were animated and leap to a higher energy level. When they leap back to their resting state, they emit a so-called light quantum. Countless atoms make these simple leaps, being animated and being in a resting state, performing quantum leaps in open space, and create bursts of light quanta with it. The color of the emitted light depends on the particular source material. With calcium atoms it is red, with arsenic atoms it is blue, and with boron atoms it is green. I will take now a boron atom as example to examine this quantum leap a little more closely. Here you can see a boron atom as a white circle. It is a boron atom B1 in its resting state. Obviously, this is a very simplified representation of an atom, but is sufficient for the relationship that I want to focus on. Now, when intense heat is produced in the explosion, the boron atom B1 is animated and leaps to a higher energy level. Now it is a boron atom with higher energy, which I would name as boron atom B2, depicted in this graphic as a green circle. When the boron atom B2 leaps back, a light quantum is emitted. After the leap of the boron atom is in a resting state, it is an atom B1 again. So far so good. The boron atom leaps from B1 to B2 and back to B1. The states B1 and B2 are clearly defined. It is either a boron atom B1 with resting energy or a boron atom B2 with higher energy. Now arises a very interesting question. What state is in between? What state is there while the atom leaps? What is a boron atom B1 or B2 during the leap, when it has leaped off and has not arrived yet? Once the boron atom B1 has leaped off, it is no longer B1, but not B2 either, because it has not yet arrived at B2. During the leap, it is neither B1 nor B2, or not B1 and not B2. When it then had arrived at the higher energy level, it has a new being. It has become a boron atom B2. The upward leaping starts with B1, goes to a state of the in-between, which is not B1 and not B2, and ends up at B2. Therefore, I could say that the atom B1 changes to a state of not being an atom, the not being, and then to a state of being a new atom B2. In this new image, I have shown the first step of the upward leaping. The boron atom B1 leaps into the not being first, and then with a fresh leap up to the higher energy level and appears there as a new boron atom B2. With the same logic, the atom B2 leaps into the not being first, then from there in a fresh leap to the resting state and appears there as a new boron atom B1. During this downward leap, a light quantum is emitted. In this next picture, I have just put together the graphics of the upward and the downward leap. B1 and B2 are considered two physical distinct boron atoms. They have different energy. But what about the not being? This not being is no man's land, where the atoms somehow seem to have lost their defined status as atoms. In order to bring more light into the question of the not being, the theory of the vacuum energy might help, which today is often associated with the so-called dark energy of the universe. The theory of vacuum energy states that an absolute vacuum, which is a space without one single particle of matter, can have a huge potential of energy. Calculations have shown that this vacuum energy is so immense that few cubic centimeters of this vacuum energy would be sufficient to evaporate the water of all the oceans of the earth. This vacuum energy is present as potential everywhere in space. This energy potential could then be the destination where all boron atoms would plunge into during the fireworks. In this potential of energy, all the atoms would then lose their matter properties and become not being. Immediately after that, they reappear in being as new atoms. Basically, this leap from not being into being seems to be possible, because in the opinion of physics, such a leap has already happened 13.7 billion years ago. This leap is called the Big Bang, in which the universe has leaped explosively from the not being into being. In this presented so-called quantum model, the boron atoms leap too from not being to being, but they do not remain in being. Instead, they leap right back into the not being and then immediately into a new being. This is a main difference to the historic Big Bang. In the model presented here, Big Bangs happen here and now continuously and not only once. Each leap of a boron atom from not being into being is like a small Big Bang, out of which a new boron atom pops up from the not being. If you imagine that this is not true only for boron atoms in fireworks, but also for all other atoms in the universe, then all the atoms of the universe here and now leap straight into not being, and immediately leap with infinitely many small Big Bangs into a new being. These leaps with Big Bangs are like a giant chaotic dance of the universe, in which each atom freshly appears in a new being trillion times per second. This view certainly is unusual because we imagine matter always being solid. We do not think that matter is constantly disappearing and reappearing in the same or different form. But this is what seems to happen in the quantum model presented here. At this point, it is perhaps appropriate to point out that this quantum model, like every other model, can only be a description of reality and never be reality itself. A model can make relationships clearer and serve new approaches to develop thinking ahead. I myself find this model very helpful, and I will come back to it in the second part of my video, where I would like to show some unusual conclusions that may result from the quantum model presented here. To conclude this first part of my video, I would like to quote from a lecture of Professor Dr. Hans-Peter Dürr, the well-known physicist and author of many books. In this lecture at the Technical University of Clausthal, he said while explaining the motion of an electron from A to B, "It's something that comes really new and then disappears. It is like the beginning of the Big Bang. It takes place continuously. The world is created new every moment, but with a recollection of the world before." End of the quote. Since we are all part of this newly created world, every single one of us is just here and now involved in this creative process of the universe.